Okay, in the last video, I will start every video in this section with okay. In the last video, we introduced the fundamental theorem of calculus, part 1, and we proved it. Now let's use it, okay? So, example 3. Just 3 parts, it's the whole video. Find the derivative of, part A is going to be g of x equals the integral from 1 to x of 1 over t cubed, well, it's t squared now, plus 1 dt. So, this is the fundamental theorem of calculus. Now, it may not look like it. Right below here, I'm going to write the fundamental theorem of calculus. And again, this is continuous. Actually, this is continuous for all x. Specifically, it's continuous between 1 and any number bigger than 1. But x doesn't have to be in that region. So since this is continuous for all x, it's a rational function. So if it's a rational function, it's continuous everywhere except when the denominator is equal to 0. And it turns out the denominator is never equal to 0 here. Okay? So the fundamental theorem of calculus says that f prime of x equals f of x if f of x equals the integral from a to x of some function of t dt. So let's try to find the connections here. So this is our function, right? In the theorem we have f. In this problem we have g. We still have our integral. Here a is 1. And then we have our function, right? Our function is just 1 over x squared plus 1 or t squared plus 1, whatever variable you want to use. So this says that the derivative of that function is just the integrand. Right? It's just that inside function evaluated at x. That's it. So I say we're taking a derivative here, but you're not actually using any derivative rules outside of the fundamental theorem of calculus. Because everything matches up just so. G prime of x is just equal, right? It says the derivative of that area function. The derivative of this integral function is just the integrand evaluated at x. And it doesn't even matter what a is, right? Remember the fundamental theorem of calculus. I wrote it just right here. Notice it doesn't matter what a is. Why is that? Think about it. We'll cover why later on in a future video. But yeah, it's crazy when we get into fundamental theorem of calculus part 2. So the next video we'll cover it. It has nothing to do with that. So it's just a function evaluated at x. Here's our function. Let's evaluate it at x, and we're done. We're done. No quotient rule, no chain rule yet. There we go. So if it's exactly in this form of the fundamental theorem of calculus, very quick. Derivatives, in some sense of the word, cancel out antiderivatives. That's one way of thinking about the fundamental theorem of calculus. If my function has an integral in it, under certain conditions, you can kind of informally think of it this way, and I want to take the derivative, well, it kind of cancels out that integral in a way, and that's why we're just left with that integrand evaluated at our variable, which is x here. Wow. What a fundamental theorem we've got here. So let's see what let's see some of the more fun that we can get on in this type of problem. Let's say our integral function is not going up to x this time. We're starting at some a, doesn't matter where a is, here a is 0. And this time, let's not go up to x, let's go up to the square root of x. And let's say our integrand is sine of t. Well, we can't just say this is equal to the sine of the square root of x. We can't just say it's equal to sine of x. We want to know what f prime of x is. Let's change lingo. That's Newton's notation. Let's use Leibniz notation. The derivative of capital F with respect to x. Well, if this were just x, we could use a fundamental theorem of calculus. So let's use a substitution. If that circled thing were just a single variable, no square root, if we could get rid of the square root, we could use fundamental theorem of calculus, no problem. Let's use a substitution. Well, if we use something with u, that's the chain rule. The derivative of f with respect to x is the derivative of f with respect to u times the derivative of u with respect to x. One formulation of the chain rule. And again, a lot of people don't prefer Leibniz notation, so this may look a little bit weird, but let's just look at what this is. Go off to the side. If u is this, what is f of u? F of u is the integral from 0 to u of sine of t dt. And so the derivative of f with respect to u, this can be the fundamental theorem of calculus directly. The derivative of f with respect to u is just the fundamental theorem of calculus, which says our integrand evaluated at our variable. It's just the sine of u. And that's the harder part. That's this guy. But what about this guy? Well, u is the square root of x. So what's the derivative of u with respect to x? You guys got that, no problem. We can take the derivative of the square root of x by using the power rule. Think of square root as an exponent of 1/2. Then the derivative of u with respect to x, bring down the exponent, and subtract 1 from the exponent. And you could rewrite this as 1 divided by the 2 square root of 2 square root of x if you'd like. Either form here is fine. I think the bottom form is more useful or easier to read right here, but the top form is more useful if we're taking another derivative. All right. Remember negative exponents, just put something in the denominator. So now we just plug in. That's going to be df du, which we said was sine of u, times du dx, which we said was 1 over 2 root x. Clean things up a bit. We introduced u in the first place. Now we have to unintroduce it. Your final answer should only have x's in it. So u is just the square root of x. And this is what we get. This is the derivative of that integral function. So it's almost the same, right? It's almost just plugging this guy in to here and being done. Because that's exactly what we do for the regular fundamental theorem of calculus. Look over here, right? We're just plugging in that variable and being done. But because that variable is not just an x, chain rule says we have to multiply by the derivative of whatever that red circle is. All right, and this is a full formal way of how that happens. In the next problem, I'm just going to jump straight to here, really straight to here. But this is why. This is the answer why. Fundamental theorem of calculus, so easy, might feel like cheating, but it's not. So let's do part C, h of x equals the integral from x to 2x. Whoa, from x to 2x, Jason. That's not from a to x. We can't use the fundamental theorem of calculus. Fundamental theorem of calculus says this has got to be a constant. Well, let's just see the rest of the problem and see what happens. T cubed dt. Man, what are we going to do? We're going to use a little property of definite integral that we talked about in the second section of this class. Watch this. A can be any real number. And if a is any real number, is this not the same as the integral from x to a of t cubed dt plus the integral from a to 2x? We had a property that said a can be anything. A doesn't even have to be between these two things, and it's still true. A can be anything, and we know that's true. Thank you, section 1.2. Thank you, properties of definite integrals. You just saved the day. And now you might be saying, all right, well, Jason, sure. That fixes this part. We can take the derivative of this part using the chain rule and the fundamental theorem of calculus. Very proud of you, Jason. Good job. But, Jason, it didn't fix this problem. It's backwards. The x needs to be on the top and the a needs to be on the bottom. Well, if only there was a way to make that happen. 1.2 comes in and saves the day again, right? Because 1.2 did give us a property. Go back to your list of definite integral properties. We can switch the limits of integration as long as we add a negative. And I said, this is kind of hard to see now with areas, but I promise we're going to use it. And here's where we're using it. The first of a few times, okay? So we want to get things in terms so that we can use the fundamental theorem of calculus. So this is the negative. We can switch the limits of integration if we add a negative. And now look at what we've got. Now we have two pieces that are perfectly in the form of the part 1 of the fundamental theorem of calculus. Now we can take the derivative. Remember, one of the themes of Calc 1 for taking the derivative is try to rewrite and simplify the function as much as you can to make it easier to take the derivative of. Now it's in a good form. It's going from a to x. On that one can be the fundamental theorem of calculus directly. Here it's from a to 2x. We'll have to use the chain rule, but we can still use the fundamental theorem of calculus. We'll be doing that second integral with this method, but we'll be taking a small shortcut. We'll still be using the chain rule, but to keep the video not too long, I will take a shortcut. But now we can take the derivative. So h prime of x. The negative is still there. We need to take the derivative of this integral. Well, this is exactly the situation of the fundamental theorem of calculus. Another way of writing the fundamental theorem of calculus, by the way, is this way. The derivative of this integral from some number to x of f of t dt equals just f of x. And another way of thinking about it is you're just putting this in for that variable, using the chain rule if you have to. So this just becomes negative x cubed, this first one. Fundamental theorem of calculus, taking the derivative. If it's just a to x, all you do is plug in that variable and you're good to go. And here, this is going to be very similar as well. Okay, we're just going to need the chain rule. So we'll plug in that 2x and multiply by the derivative of 2x. Sorry, we're going to multiply by the derivative of 2x, which is just 2. So if we plug that in, that's just 2x cubed, right? Wrong. I made a mistake here. I'd recommend pausing the video, try to figure it out if you can see the mistake I made here. We need to plug in the 2x for t, but t is getting cubed, so the whole 2x needs to be cubed here. And now we can just simplify and be done. The negative x cubed plus this becomes 2 cubed, which is 8. 8 times 2 is 16. And x cubed. We have 16x cubes. We're losing one of those x cubes, so now we only have 15x cubes. And that's our derivative right there. There you go. That's some example problems for the fundamental theorem of calculus, part 1. We'll get into part 2 in the next video.